Hi, good morning. I'm sorry it's yellow. It seems to be some sort of connection issue. So I hope it's legible enough. But I didn't deliberately mean to hurt your eyes. Okay, so today I'm going to talk about some of the things in the AstroPy project that may be of use to the general scientific community. The AstroPy project, and Tom Aldcroft talked about this in much more detail yesterday, is a project to bring together a number of disparate astronomy-related Python projects under one roof, make them more consistent, and then make them work much better together. Certainly the kind of the next wave, I think, of work on AstroPy, it's going to be integrating all these things much better so they work as a cohesive unit much better. But in any case, I'm going to be talking about three different things today. Units. We have a physical unit framework within AstroPy. I'm very interested in the talk after the break that's also about physical units. It'd be interesting to compare notes there. Then I'm going to talk about something that's really the work of Nadia Dencheva at the Space Telescope Institute, which is a new models and fitting framework. And then lastly, I'll talk about something that Tom Aldcroft has kind of led, which is a table library, a flexible table interface. Okay, so starting with the units subpackage, there's a whole bunch of Python-related physical units packages out there, and we looked at most of them, seemingly all of them, and there were sort of three features that none of them had that kind of led to us going our own way. We did actually end up starting with a project, the unit library from PyNbody, so that's kind of its genesis, but it's changed so much since then it's hard to call it the same thing anymore. So anyway, these are the three features that we really needed for astronomy that led us to go our own direction. We wanted to have a separation and conversion between systems, so some astronomers work in SI, some work in CGS, and they want to work in either of their spaces, but then you do need to be able to convert between the two when you need to do that. We also wanted to have something that dealt well with equivalencies. So it's very common in astronomy to talk about frequency and wavelength as being convertible, but of course one is the inverse of time and the other is a length, and strictly they are not the same thing. So it provides kind of a backdoor to treat those as equivalent when necessary. And then we also need to support all the different ways of spelling units, the serialization formats for units that exist in astronomy. No one seems to really agree on how you should write a unit. There's VO unit project underway is trying to kind of resolve that, but in the meantime we have the imperfect world in which there's all these different formats out there. Okay. I'm not sure, maybe if I can, there we go. Okay, that gets rid of those scroll bars. Okay, so this is how you import the units, and within there's units. So that's the meter. You can read the doc string. It says it's the base unit of length in SI. I'm sorry about those scroll bars. I'm not sure why they're appearing and why I can't get them to stop. There we go. And you can convert between them, so you can convert a parsec to a meter, and that's the correct result. You can look up their physical type. That's all sort of determined on the fly. You can list all the equivalent units that we have. We have a bunch of sort of a random selection of imperial units in there. One of the things we're working on now is not throwing all that stuff in there and making it easier to just pull in the units you want to use, but that's forthcoming. It's very easy to write custom units. So if you want to make miles per hour, you just simply say mile divided by hour, yard divided by fortnight. This is all stuff that most of the Python unit packages do. They overload the operators. And, sorry about that. The keyboard isn't working for me either. So we have a system of equivalencies that I had mentioned. So normally, if you convert a nanometer to hertz, you get an exception. That nanometer is a length and hertz is a frequency, and therefore it's not convertible. However, If you provide an equivalency, in this case the spectral equivalency, then it works. It knows how to do that. And we provide a bunch of different built-in equivalencies, certainly ones that are more complex than this. It's easy to add your own equivalencies. And this equivalency stuff also works when you try and find equivalent units. So when you look at all the equivalent units of hertz, but you provide this equivalency, you get lengths, you get calories, all these things that it can convert to given that equivalency. Oh, pardon me. So you can decompose these units and see what they're made up of. So here's the Rydberg. It's a unit of energy, and it decomposes into this. You can also decompose to units that are not, you can decompose but not all the way down. If you want to see it in terms of newtons and meters, you can do that just by providing bases. So for any unit, you can provide a list of bases, and it'll decompose into those bases as best it can. And this last part is the system handling, right? So you have SI and CGS, these two sort of competing systems. And you can take something in SI, meters per second, convert it to CGS, and it gives it to you in centimeters per second, which certainly is sensical. It also gives you this correct but very strange unit. But it's doing the right thing. It just sort of, it doesn't think like an astronomer just yet. So anyway, that's the units part of my talk, and there's my email if you have any further questions. Now I'm going to move on to the models and fitting package by Nadia Dencheva. Its main reason for being, and the reason we're sort of not using something like the SciPy fitting stuff directly, is we wanted to separate out the models from the fitting algorithms and allow you to plug, when sensical and when it makes, when it will work, plug any model into any fitting algorithm and just have it work. We also have a strong need to replace WCS, the World Coordinate System, over time for the non-astronomers. We have a need to replace that over time, and models is probably going to be the basis for how we do that. So you import it, and creating a, sorry, I'm pressing the wrong button. Here we go. Okay, so these are the fitters that we have now. We don't have very many, but we're going to grow them. It's really just sort of the beginning of the framework at the moment. You create a model. This way here I'm creating a one-dimensional polynomial model of degree 3. And you can set parameters on the model. And to evaluate it, you just call it like a function. So here's my model, and I give it some input, and then I can plot it, and you see there it is. Okay? That's not terribly exciting. That's just a third-degree polynomial. Where it gets exciting is when you start to combine that with fitting. Sorry, it's this one I want. Okay. So let's add some noise to the data. We had that data, the perfect curve. We've added some noise. And then let's see if we can fit it back. So here we're taking a least squares fitter on the noise data. I'm sorry to be doing the scrolling around. It didn't capture my keyboard events for some reason, so I can't do it that way. This is the solution from the fitter, and obviously the parameters are different, but if we plot it, you'll see that we get the same thing. So the light blue is the original model, green is the noisy line, and the red is the fitted line. And you see it's done a pretty decent job fitting it. So it's a very simple interface, and that's sort of the point of the library, is that you just have these models, you feed them into a fitter with some data, and it goes to town. You can also put constraints on the model, and the fitters will understand those. So you can say which parameters are supposed to remain fixed. You can specify an arbitrary relationship between any of the parameters just using a function. You can put bounds on the parameters. You can do minimization and maximization points on the models as well. So here, just as another example, we're setting the amplitude of this Gaussian model as fixed. And then when you go through and this one there, and then you can print them out and see that they're sorry. Then you can run it through the fitter, and you see that it's left amplitude alone, right? So it does the fit, but it's not going to use all the parameters in order to perform the fit. And lastly, you can combine these models. One of the things we really want to do with our replacement for WCS is be able to say the model is perform this transformation, then this one, then do these in parallel, come back and do a few more. You want to be able to basically build a tree of models to create this composite model, and it allows that. So here I'm plotting an ellipse, and I'm going to transform it in a few different ways by scaling it, translating it, rotating it. And then you can take those three transformations and create a composite model out of it, and just run that as if it were a non-composite model. They behave exactly the same way. And of course, you can build composite models out of other composite models. So that's the end of the modeling part. Again, I didn't write this code. I've just kind of followed it. Unfortunately, Nadia couldn't be here due to NASA's travel budget restrictions right now. So if you have further questions, I encourage you to email her. Okay, and the last part is on our table subpackage. This was written by Tom Aldcroft, who's in the room. It began life as @PI and then was brought into astropy. It basically adds a common layer of functionality on top of NumPy structured arrays, making them a lot more flexible. I mean, anyone who's worked with NumPy structured arrays knows that you can't really resize them. It's very tricky to add and remove columns. You basically end up having to, destroy the thing and start over again. And within astropy, we brought in PyFits, which of course has a table class of its own that does some of the flexibility, but it was sort of incomplete. And then we brought in VO table, which had its own table class, which did a different set of things and not very well. And so the reason we have this table class is to just create a nice, clean interface that's very flexible for tables that everything else can use. We don't have to worry about reinventing that wheel over and over. We did, of course, look at pandas, which is a common way to deal with tables in Python. There were a few shortcomings. Whether those can be resolved or not down the road is an open question. In the meantime, we kind of did go our own way on this. Pandas doesn't support multi-dimensional columns, which is a very common thing we need to deal with. So within a column, each entry is itself an array. It doesn't have very good metadata support. And for missing values, we needed to use masks rather than nans, because we need to preserve that distinction. So you can initialize these tables from all kinds of things, and it just kind of figures it out. Every sort of form of input data is uniquely identifiable, so it just generally does the right thing. So you can initialize it from a list of columns. So here I just have 3 lists, put those inside a nested list, and feed that to the table constructor. You have to give it the names of the columns, or you generally would want to give it names of columns. And then you print it out. You see we have a little IPython thing that displays it nicely. You can initialize from a list of rows. So this is a list of dictionaries. It means that it's row-oriented data. And or a dictionary of columns. So you give it a dictionary where each key value pair is a column. So column A is this, column B is that, etc. I'm really sorry about the scrolling. I can't get it to connect to my keyboard for some reason. You can also initialize from a NumPy structured array, of course, which is what it is under the hood. Then, of course, this is kind of the magic. You can modify these tables in various ways. You can delete columns. You can add columns. You can, delete a column again. You can rename the column. You can add a new row. So all these things that are kind of tricky with raw NumPy structured arrays are quite easy. And again, we handle masked values. We use NumPy masked array. Obviously, when there's something better out there, we'd love to switch to it. But it is something that handles missing values as a mask, which is important. You can change the formatting of these tables. So you can just set the format of a particular column to use 4 decimal places and then print it out. That example is somehow wrong. Sorry about that. It does this pretty printing of the table that's a little different from what NumPy does by default. It'll actually show the beginning, both sides of the table and both the top and the bottom, and skip the middle rather than just showing the beginning. And then, of course, because this is astronomy, we have all these different formats we need to support. And the table, we have readers and writers for all these different things. There's a bunch of different ASCII formats there. The binary formats fits in HDF5, of course. We punt out to H5Py library for that. And we also support VO tables. And it's very easy. It sort of figures it out on the fly. If you just give it a path to a XML file, VO table XML file, it figures it out. And you can even pass it a string, which is the table data itself in a ASCII format, and it will figure that out. And then there's also some sort of database operations that are in there about these tables. Given these 2 tables, so I'm just show them there. We have an optical, some theoretical optical data and some X-ray data, and you can do a SQL join on them, and that's kind of just built in. It also you can H-stack and V-stack the tables. So and you can join, and you can even provide an explicit list of keys when you do the join. And that's the talk. We have some time for questions, and Tom is here, so he can take questions for table if there are any. Yes?
Yeah, that's coming. I mean, this is another reason that we kind of wanted to go our own way.